that, and then today we are actually coming closer to the embedded systems, which means, well, your smart systems, a different kind of devices that does things, and there are some considerations on the digital filters when you're putting those in anything else than a high power computer. Okay, although these embedded systems also start to have quite high power, but anyways, the same issues will be there, plus some others. Okay, but anyways, so basically one issue with the smaller devices is about performance and how actually the device can manage to do all the stuff it's designed to do, and basically this any digital filter implementation requires a lot of multiply and accumulate the operations. For example, if you have a direct form FIR calculation, it's basically just a sum of those the impulse response points times the data vector. So basically you would need to write something code similar to that one. So basically you have a pointer pointing the input data, another pointing to the output data, and basically for each output point you would calculate that loop. Loop calculates the sum of those multiplication of those terms. Okay, that's a simplest way of doing the the FIR for a symmetric the impulse response. As you see, I am not actually reversing the time there for a good reason. So on convolution you should reverse the time of the other one, but if you have a symmetric, it doesn't matter which way this one would be. So I have two thumbs. Okay, some people don't have even one thumb. Okay, but anyways, the so it doesn't matter which way you are doing the sum for the impulse, for example. So basically that's why I have the bk times xk there. Okay, and summing to the current output pointer position. Good. So that's basically requires a lot of additions. Additions are usually quite fast, even for software. If you are doing it, for example, floating point with software, it's relatively fast, but the multiplication usually takes a few clock cycles more on general purpose processors. Okay. But how these Mac operations are done depends highly on the processor architecture. So floating point implementation would be easy for the design point of view, but basically usually the fixed point gives better performance per energy. Okay. So basically if you are taking any good modern embedded controller or microprocessor, they actually have some Mac units there already. Some of the processors have nothing else than Mac. For example, the video processing blocks, they basically have pipelined parallel Macs. That's it. That's what you need to do when you are doing any of the video calculations. So, but anyways, to employ that Mac unit, some assembly programming may be required. So this is like IKEA furniture. Although, say, if you have a good processor with good support from the compiler side, then of course you will be on safe side. So you don't usually need to think of if there is a Mac or not the compiler and the linker knows it already. Okay, and then about the hardware or software. As I mentioned, the floating point is easy to design, and then you don't have any artifacts from the or effects of the value quantization or digitizing effects there. But if you have a simple 8-bit processor like PSOC1 processors or the Arduino has, is it 8 or 16 bits? Anyways, it doesn't have any floating point unit there. So those small general purpose processors, they usually don't have a floating point unit, which means that making a single precision floating point would require thousands of instruction cycles. Meaning that, okay, you can still use it as long as your sampling rate is not, high, or you have extremely high clock rate on your processor, or in some case, actually, for example, these software-defined platforms like these FPGA circuits with some software-designed things. Then you can use a parallel processing on smaller bits, and then actually you can do a lot of things on those with a higher clock rate. Okay, and then there are actually some special kind of things, since the digital signal processing is quite, those tasks are quite common on embedded systems. So basically, some of the embedded controllers have so-called fused multiply add acceleration. Basically, it's just a special hardware to do just that floating point multiply accumulate in a single cycle with rounding. Okay, basically the chip designer has already decided how to round these numbers, and well, those are usually used on this kind of platforms. The mobile phone processor, we also have some video capabilities already on the processor itself. Okay, then there are special processors which are called digital signal processors. Basically, those are just processors which have been optimized for MAC calculations, nothing more. So multiply, accumulate, process, which actually also means that they use heavily also apply the parallel processing and also pipelining. Have you taken the chaos course, the modern computer architecture yet?
Yeah.
Excellent. Okay. Parallel processing and pipelining, heavily involved in digital signal processing or processors. Okay, and those are still used for on embedded systems, which are requiring a lot of signal processing, because they are the most cost-efficient way of doing the processing. Meaning the amount of energy they take from the battery would be much less than from doing the same thing with a general purpose processor. Although you might get much better performance from the general purpose processor, but performance per the cost, when the cost here is the energy consumption, the digital signal processors are much better on that one. Some applications areas for digital signal processors actually is automotive industry is using those heavily. Although also video acceleration or audio processing on any handheld device. The special processor may actually say, okay, this is a audio codec with some filtering properties. Well, in reality, it actually has a digital signal processing block on it, which does this thing. Okay, good. And then to the effects. So basically, we have the quantization of time, which gave us the not digitized, but the sampled signal. This far we have been just looking after sampled signals, since double precision floating point is enough of calculating almost everything with the high precision. But when you are actually starting to quantize the parameters on multiply, accumulate cycles, okay, meaning that you are not using that the parameters as they are, but the closest rounded number to that certain precision. And that's a picture what happens to this same filter. So this is, I think it's the some of this classic, it might be elliptic, or, well, it doesn't matter. It's a 1, 2, 3, 4. So it's 8th or 9th degree filter. And quite nice when you have a floating point accuracy. But even when you are dropping that accuracy to 16 bits. By the way, what is the accuracy of the floating point? IEEE double precision floating point. How many bits? No, much more. 40. 40. 40. Yeah, single precision is 20. And then there's the exponential and mantissa. Mantissa has the value of, and that's 31 bits. Then sine bit, and then 8 bits for the exponential. I think. I might be wrong though. You might better. You might actually check it from the internet. But anyways, the double precision floating point, it still has some, inaccuracy on it. But it's so small that it doesn't usually, you don't need to care about when you are doing the calculations on a high power computer. But when you are doing a fixed precision, meaning integer logic or integer precision calculations, for example, 16-bit calculations, for this same filter, you can already see that there's something happens on the for the edge of the filter here. So it's not anymore the same as what we designed. And even worse, when we are going to the 8-bit calculations, then we actually are losing the filter properties more or less totally. So it's not anymore the same. Okay, and in a bad case, actually, when we're thinking of the IIR system, and you start, if you have a pole very close to the unit circle on your floating point, ideal kind of system, when you then start basically quantizing the filter coefficients, the poles actually can move outside of the unit circle, and suddenly you have unstable system. Not good. Okay. All right. So basically, there are some. If there is some sort of say fault, then there's always some things that we can use to fix it. So fundamentally, what is feedback system? Huh? I have no idea. I have. It seems that this is under construction. The last line doesn't make any sense. The feedback system is a system with feedback. Okay, good. Okay, but anyway, so the two big choices you have here. If you have a big system you can actually have two kind of well, let's study from the other side. Okay, so let me. I think I need to use some whiteboard now. All right. So combining the systems or combined systems. So if you have, say, two systems, H1 and H2, in series, this would be systems in series. Basically, this one is the same as, okay, this one is HZ, this is H2Z. So the combined system actually is the same as H1Z times H2Z. So if you have a cascaded systems, then you basically just multiply those. So this is used the other way around in reality. So any system, if you think of the zero pole plane, if you have multiple poles and zeros, you get better calculation accuracy if you start doing the this kind of partitioning of the system. Take those zeros and poles in one system and then take these to the other system. And just basically you have two second order systems. So that's basically second order system division. And why you are getting a better calculation accuracy? Well, because of the parameters are much closer to each other. The filter coefficients are within the same decade when you do the splitting like that, compared to well, FIR would be even better example here, where you have, say, well, I need to show it on the MATLAB basically. So on the FIR system, let's see. Okay, so that would be IIR. Then if we have a FIR system with the impulse response symmetric like that, and these will go very small here. You have seen these before, for example, on the FIR the exercise. You needed to plot the impulse response, I think, was it there? But anyways, the magnitude of this one could be totally different order than that one. Okay, meaning that when you're doing the calculations, this could actually be less than the calculation accuracy, but it still affects on the system behavior. But if you do the zeros and poles, well, the poles are here of the origin, but then the zeros, okay, zeros, for example, like that. Okay, and do the second order systems. One second order system, another one, third one. Oh, that's fourth order actually. But anyways, second order would be half of that one. Do the second order system division here. Okay. And calculate the parameters. They are within the same magnitude, guaranteed. Okay, which means that on the second order system you have much better accuracy on the combined system.
So does it mean that you can use less coefficients for the second order to get it good enough.
Yeah.
For that reason, you don't have to have so long filter.
Yes.
If you have a really
Yes.
long
Yes.
filter, your coefficients are going smaller
Yeah.
at
Yeah.
the edge of it.
Yes. Yes. But now you have plenty. You have yes. You, exactly. So you have less. Well, you have shorter filters, but you know more filters, cascaded. Yeah, cascaded filters. And each of the filter is actually a pretty accurate already there because of the rounding errors doesn't add up that way. On cascaded, it more or less it's they're suppressing each others. Especially on the other side. So this is the cascaded system. But then actually you can always do the parallel system. Meaning that although the design will be a little bit, say, by pen and paper it will be hard, but with the computer this is also a piece of cake. So h1 of z and h2 of z. And basically this is same as h of z equals h1z plus h2z. Okay. This is used mostly on the case of IIR, since on FIR you would just have, you know, it doesn't really add up. Well, a little bit, yes, it would help a little bit on the calculations. You just have to rescale the filters, so basically take a couple of those, each of those, and add some elements and do the final calculations at the end. But it doesn't affect that much on that, on the FIR calculations. On IIR, this adds a lot of the good things, although it's heavier to calculate. This way it's easy to calculate if you have, say, that sum of b k zt minus k divided by ak zt minus k plus, okay, ck zt minus k d k zt minus k. Okay, as you can see, you can actually calculate it forward by, basically this would be multiplied with that, and this would be multiplied both upstairs and downstairs by. But it gets a little bit awkward that way. But yes, you can do the parameterization also for parallel systems, and with the computer it's this would, in addition to breaking down the systems in the second order sections, okay, in addition to that one you would add some say stability also by this summing these outputs. So that would basically, it would be some sort of average of the outputs, which reduces the error. Okay, but it's that, well, you already can see it on simplest case. Basically, you would start by knowing this one and then trying to figure out how to basically construct the parallel sections. That's not straightforward task anymore. Okay. But anyway, so we have the cascaded second order system is the most common way of breaking down any FIR or IIR system, so that you can calculate it with a higher precision or less rounding errors. Let's put it this way: less rounding errors.
Use any multiple accumulation units anymore if you have cascaded it?
Yes, yes, you can.
Okay.
but then it has to be designed for this kind of system, since, for example, the those digital signal processors, they have some special registers to actually, even if they have just single MAC unit, which is, well, ancient processor though. But digital signal processors has plenty of, they have multiple MAC units. So basically the parallel processing, perfect. It's perfect for this one. And pipelining and parallelization of this one. So that looks like a pipelining. So
Just thinking that if you
yeah.
have, for example, a really big field filter at first,
Yeah.
you want to piece it down to the second order systems.
Mhm.
In the end, you have like 20 different filters that are
Yeah.
to each other,
Mhm.
and you always
Then-
have to compute the first one and the second
Yeah.
and the third.
Yeah.
So
Well, yes, you can, but basically that then you'd also start blocking, making the blocks out of there, not processing single point at a time or single sample at a time, but use it basically run it, for example, some 128 data points first, and then move it to the next block and so on. So then you don't have to shuffle the data back and forth. Or, well, you can always, if you have a fixed filter, then you have subroutines, nested subroutines with their own local memory. Yeah, it can be done. Oh, right. But anyways, so second order sections has smaller quantization errors than the direct system, period. So if you are doing implementation on fixed precision system, SOS, help me. Yeah. Okay. It would have been nice if I had a okay, so this is FIR system showing 8 bits precision of floating point, and then that green one is actually a 8-bit precision direct form, meaning it has a lot of rounding errors because of these are rounded more or less to 0, or the relative error on these are much higher than on the higher values. And then if you are actually using 8-bit second order systems, you are basically getting the same performance as the floating point. Ha! Okay, so does it pay to make this division? Yes, it does. Same thing also for the SOS and IIR filter, and this looks quite similar as I had on the first picture. So the blue one is the original design, and then the 8-bit has had the problem on this edge of the filter, and also the looks like there's some error also on the stop band. Also, that's not a bad error. But then if you're doing the second order system division, you have relatively saying it's better design now. Not perfect, but much better than the this direct form. Okay, good. So that was the theory part. Short theory today. By the way, did you get my message about the IIR system? So the deadline for that exercise is on Friday, because I didn't have a, well, I had a link. I could open it, but nobody else. The classic error here. I checked it works, but I checked it on, while I was logged in the Google. So of course I see all of my, the videos there if I'm logged in, but I didn't publish it. A small mistake. But anyways, that's life. So let me do something here.